In section 9.4, we're going to define and explain effusion and diffusion, and then we're going to talk about Graham's law and how to use it to compute relevant gas properties. So a little recap here. What we experience as gas pressure in macroscopic domain is due to gas atoms and molecules colliding with objects and each other in the microscopic domain. When these collisions are frequent, or the gas atoms have a lot of kinetic energy, we experience a high pressure. And we're going to recall that the kinetic energy of a gas is directly proportional to its temperature. So one way to describe the frequency of collisions is to talk about the distance a gaseous atom or molecule travels without colliding. This is known as the mean free path. The mean free path is the average distance a gas or atom molecule will travel in a particular system before it hits something and collides. It is typically hundreds of times the diameter of a gas molecule. Diffusion. So whenever possible, matter is going to spread from an area of high concentration to an area of lower concentration. To put this in more scientific words, the matter moves across a concentration gradient from an area of high concentration to an area of low concentration. This process is called diffusion. Some examples are like smells spreading through a room or a drop of food coloring spreading through a glass of water. Because gases are moving rapidly and freely, they will quickly spread through the container. And diffusion only stops when the concentration of gas is uniform throughout the container. So we can picture this here. If we had hydrogen in the left chamber and oxygen in the right chamber and a closed stopcock, we open the stopcock, allowing the two systems to come in contact. Some of the hydrogen moves into the right chamber, some of the oxygen moves into the left. And after a long time, relatively long time, we get an even distribution of hydrogen and oxygen in the two chambers. The rate of diffusion is the amount of gas passing through an area per unit time. So we have rate, and we have an equation here for this. Actually calculating the rate of diffusion is kind of tricky because it depends on a lot of factors. The magnitude of the concentration gradient, the amount of surface area available for diffusion, the distance the gas molecules must travel, and the velocity of the gas molecules. Effusion is the process of a gas moving through a small orifice. It's similar to diffusion, however, the two rates are not the same. Graham's law of effusion relates the rate of effusion to the atomic mass of the gas. So we can see that here we have the rate of effusion, and this means that it's related to, and not necessarily exactly equal to, 1 over the square root of the atomic mass of the gas. We'll note that the rate of effusion decreases as the mass of the gas increases. So here we have diffusion throughout the container, and we're picturing effusion as there's a barrier with a small orifice and some of the gas is allowed to go through it. We can do some calculations with Graham's law. We can calculate the ratio of the rate of effusion of helium to the rate of effusion of argon. So one compound to another. And if we divide those two rates and do a little math, we'll see that that's going to be equal to the square root of the atomic mass of argon divided by the square root of the atomic mass of helium. Note that here helium is in the numerator and it appears in the denominator on the right hand side. If we plug in those values that we already know, we can get that the ratio of those two rates is 3.159. So let's go through an example where we can get some useful information from that. So here we have two identical balloons are filled with the same pressure and volume while being held at the same temperature. One is filled with helium, the other with argon. The argon balloon takes 4 hours to lose half of the moles it contains, N. How long will it take for helium balloon to lose the exact same number of moles? So the first thing we need to do is to relate the rates of effusion to the time it takes for the effusion process to happen. So the rate of helium effusion is going to be the number of moles that travel divided by the time that it took, and the same for argon. And our problem, we said that it was going to be the same number of moles. How long does it take for the same number of moles to come out? So these two ends are the same. We can cancel those and we get this relationship here. If we clear those complex fractions, we get the time of argon divided by the time of helium is equal to 3.159. Plugging in the time that it took for the argon to effuse out, we get this relationship here, and then solving for the time of helium, we get this, and we see that it would have taken the helium 1.266 hours, which is what we would expect. We'd expect that a molecule with a lower atomic rate is going to effuse quite a bit faster. If we picture that, that's pretty much what's happening in the case of a balloon. Gas is slowly effusing out through tiny orifices in the surface. If we had argon and helium, or helium and argon, we would see that the helium starts to effuse out quite a bit faster. And effusion is also the means by which they enrich things like uranium. In this case, we are enriching uranium hexafluoride by basically putting it into this giant centrifuge and then allowing it to spin really fast, and it goes through a selective barrier, and we wind up with getting enriched uranium effusing through at a faster rate and purifying the gas.